A diver jumps off the platform, which is 32 feet above water, at a velocity of 16 feet per second. Let's write an equation to model the height over time for our diver. I'm going to call this the position function. It will give me the position or height of the diver at any time that I want, any time that he's in the air. I usually label that with S of t, but you could also do H of t for height. S of t is equal to negative 16t squared plus, what's the height of the diver? I'm sorry, the velocity of the diver, pardon me. 16t plus 32 for the height. Let's think about what each of these different values represent, each of these three terms in our position function. This is the starting height or starting position. He jumps from a beginning height of 32 feet above the water, right? The 16, where did the 16 come from? Velocity. The velocity. So for every second, how much higher does he go? 16 feet, right? Per every second, he's going to gain an additional 16 feet in height. Now, what's eventually going to happen? Going to come back down, right? If he jumps up, what goes up must come down. So what does the negative 16 indicate? Because what effect is also happening to the diver?
Losing.
Because of what physical phenomenon? What goes up must come down according to gravity. Negative 16t squared is the constant to account for the acceleration due to gravity. Isn't it like negative 4.9 in meters? Is that a Mr. Armstead class? Negative 4.9 meters per second. Right, but then you have to do it's 9.8 is the same as 32. It's actually negative 32 feet per second as the acceleration due to gravity. We'll kind of see why this is negative 16 when we get into integration later on in sentence. It's half of it. 16 is half of 32, just like 4.9 is half of 9.8. We're using imperial units in feet, so we'll use 16 instead of the 4.9. Effect of gravity, because this is negative. Gravity is going to pull the height of the diver down towards the water. It's going to decrease the height over time, so I have a negative coefficient. 16 is the rate of change. Per every 1 second, the diver's height increases by 16 feet from an initial height of 32 feet in total. We see where that's kind of coming from now? That position function or equation to represent the height of the diver. Okay. I have a model on Desmos with this graph showing the height of the diver over time. You can see that the diver starts from 32 feet. He starts to jump up, reaches his apex point, and then comes back down and hits the water sometime. We have several different questions we have to answer about the diver, his position, his velocity, his acceleration, etc. All right. First up on this question here says, I want to find the average velocity on the following time intervals. What's the diver's average velocity between 1 and 1.5 seconds? What's his average velocity between 1 and 1.1 seconds, and so on? What does average velocity mean? For example, when I go to Iowa City to see the Hawks play a football game, it takes me 2 hours to drive 100 miles. So what's my average velocity? What's my average speed? 50 miles an hour, right? It's total distance divided by total time. Does that mean that I'm driving 50 miles an hour for every single moment that it takes me to drive to Iowa City? No, that's ridiculous, right? Sometimes I'm going faster, sometimes I'm going slower, but on the average, it takes me 50 miles an hour for my total trip, right? That's the difference between average rate of change and instantaneous rate of change. Whether I want to know the average speed over an interval or the speed at a particular moment in time. Let's look at this applet up on the screen here to kind of see more. Instead of the diver, let's look at the height of a balloon here, for example. The balloon goes up and down in relation to the observer on the cliff, and its height over time is tracked on that blue graph below. Okay, let's visualize the average rate of change. Average rate of change is just going to be the difference in the height between two times divided by the total elapsed time that it takes to change between those two heights. Just like it was total distance traveled divided by distance it took me to drive to Iowa City. As I move these points around, I can change the average rate of ascent, the average velocity of this balloon. Now it has an average velocity of negative 1.45 feet per minute because its total change in height was negative 36.42 feet divided by 25 minutes. What if I want to find the speed at exactly 1 moment in time? I need to take these 2 points and bring them together so that there is no difference in time. T2 minus T1 would be 0. So here on this graph below, the slope of the secant line, the change in y over the change in x, the change in height over the change in time, the slope of the secant line tells me the average rate of change. If I want to find the actual speed or actual velocity at 1 moment in time, I need to take these 2 points and bring them closer together. And I end up creating what? What's that purple line called? Tangent line. Tangent line indicates the derivative, right? The slope of the tangent line is the same as the slope of the graph, which is the same as the value of the derivative at that particular point. If you want to find the average rate of change, just do change in distance over change in time. If you want to find the rate of change at 1 instant, at 1 moment in time, you need the derivative, right? All right, so let's come back to where we left off with the diver. I want to find the average velocity. Average velocity is the change in distance. This little triangle is the Greek symbol delta, meaning change in distance over change in time. I want to figure out how far the diver went up or down between 1 and 1.5 seconds. So let's use our position function. S of 1.5 would tell me the height of the diver above water at exactly 1.5 seconds, right? When I plug 1.5 into here, it would give me the position or height of the diver at that moment in time. Minus S of 1. When I subtract off the height of the diver at 1 second, the difference in these two values would tell me the total change in height between 1 and 1.5 seconds, right? That's the change in the distance that the diver has fallen. Divided by the 1/2 second difference between 1 and 1.5. I'm going to grab my calculator here, and let's figure out where the diver's at both 1 and 1.5 seconds. Negative 16 times 1.5 squared plus we had 16 times 1.5 plus 32. So at 1.5 seconds, the diver is 20 feet above water. Now let's figure out the height of the diver at exactly 1 second. So I'm going to change these 1.5s to 1. 32. What's 20 minus 32? What does that mean in context? He fell 12 feet. He is 12 feet more closer to the water at 1.5 seconds than he was at 1 second. At 1.5 seconds, he's 20 feet above water. At 1 second, he's 32 feet above water. So the two, he fell 12 feet total. How long did it take for him to fall 12 feet? 0.5 seconds. How many halves are in 12? What's 12 divided by 0.5? What's 12 divided by 2? Go the other way. 24. So negative 24 feet per second. Does that mean that he's traveling at 24 feet per second at 1 second? Is his speed 24 feet per second at exactly 1 second? No, that's not what average rate of change tells us. Just like I'm not driving 50 miles an hour the entire time it takes me to drive to Iowa City. It's just that this is my average speed. Why is it negative? Obviously. He's going down. Got that. Let's do the same thing for 1 and 1.1. Let's figure out how far he fell. What's the difference in position between 1 and 1.1 seconds? Divided by the total elapsed time, the 1/10 of a second it took him to fall that far. All right, so 1.1, when I plug those time values into a position function, I get 30.24. Negative 16 times 1.1 squared, plus 16 times 1.1, plus 32. When I evaluate the position function for a time of 1.1 seconds, I see 30.24. The diver is 30.24 feet above the water after 1.1 seconds that he left the platform. S of 1, that should still be the same 32 from earlier. What is 30.24 minus 32? Negative 1.76. So in the 1/10 of a second elapsed, he fell 1.76 more feet closer to the water. So I divide the two, the total change in distance divided by the total change in time, I'll have the average velocity of our diver. What should it be? Just move the decimal. Negative 17.6. Feet per second as our label for velocity. Why is it slower? Why is his average velocity more between 1 and 1.5 seconds than between 1 and 1.1 seconds? More time, right? Gravity's had more time to take effect, so he's going to pick up more speed the longer he's in the air. We've got some average velocity taken care of. Question number 1 so far. Okay. When is the diver's height 35 feet above water? I want to know at what time is the diver 35 feet above the water surface? What do I do? How can I use position function to answer this question? Do I plug in 35 or do I set equal to 35? Set it equal. It's just the opposite, right? I plug in a time to find the height. Now I can substitute in the height to find the time. So when is 35 for the height equal to negative 16t squared plus 16t plus 32? Make one side equal to 0. I think I can subtract 35 from either side. (32 minus 35 is negative 3. So somehow we need to solve negative 16t squared plus 16t minus 3 equals 0. Factor, we could do quadratic formula. It might factor. What is 16 times 3? 48. So what multiplies to make 48? That adds up to be 16. 12 and 4, they're each positive.
Equal what, 48?
Let's do this. I don't like the negative 16. Let's just switch the sign. Let's make it positive 16t squared, negative 16, and positive 3. It'll factor better now. I'll just reverse the sign, divide everything by negative 1. 16 times 3 is 48. What multiplies to make 48? That adds up to negative 16. You said 12 and 4. But if I have negative 16, they need to both be negative now, right? So let's call this 16t squared plus 12t plus 4t plus 3. I just for negative. Is that the same as what was up above earlier? It's just less simplified, right? I replaced negative 16 with negative 12 and negative 4. We're going to factor by grouping. From 16t squared and 12t, I can factor out a 4t. Leaving 4t minus 3. Which means that 4t minus 1, one factor. 4t minus 1 is one factor, as is 4t minus 3. If 4t minus 1 times 4t minus 3 equals 0, that means that either 4t minus 1 equals 0 or 4t minus 3 equals 0. At 1/4 second and at 3/4 second. At both 1 and 3/4 seconds, the diver is 35 feet above the water. Why would there be 2 times? Why would there be 2 times where his height is the same thing? You bet. 1/4 second, he's yet to reach the top. At 3/4 second, now he's on the way back down. So at 1/4 second and at 3/4 second, the time that we just solved for, his height above water is 35 feet. Sound reasonable? Okay. Now let's try some other stuff here. When is the diver's velocity? What is the diver's velocity when he is 35 feet above the water? How is this question on number 3, what is the diver's velocity when he's 35 feet above the water, different than the average velocity we calculated back on part 1? Okay, I'm sorry?
Oh, I just said that it's like.
So rather than an interval of time between 2 points to find the average velocity, now we just have 1 moment in time. How do I find the velocity at one exact instant, at one exact moment in time. This is an instantaneous velocity. We'll go back to that balloon. How did we take the average rate of change with this secant line in green between 2 points? Between time 1 and time 2, between 2 points. How did I take that average rate of change and find the instantaneous rate of change? I changed this secant line into a tangent. Make the difference between time 1 and time 2. 0. Therefore, if I want to find the rate of change at one point in time, what do I have to know first? In order to find the slope of the tangent line, I have to know the slope of the graph. I have to know the slope. I have to find the derivative. I want the velocity function. Is velocity the rate of change in height over time? How do you understand velocity? Is velocity the rate of change in height over time? Like 5 feet per second. What does that mean? So it's changing its height 5 feet. It's changing its position 5 feet for every 1 second, right? So velocity is the rate of change in the height. Therefore, the velocity is the derivative of the position function. To find the velocity at any point in time, take the derivative of the position function, because velocity is the rate of change in the position. So if I want to find the velocity of the diver when he's 35 feet above the water, I need to first take the derivative of the position function. So take the derivative of this piece here. What's the derivative of negative 16t squared? What's the derivative of the 16t portion? What's the derivative of 32? 0. Don't worry about that. Now, just like I can plug in a time to the position function to figure out what height they're at, I can plug a time into the velocity function to figure out how fast they're moving at that one point in time. I need to know what times. Which 2 times am I plugging in to find the velocity of the diver when you've got 35 feet above water? 1/4 and 3/4, ones we just saw for in the previous one. Let's find the value of the velocity function at 1/4 second and at 3/4 seconds. Negative 32 times 1/4 plus 16. That's negative 8 plus 16, or 8 feet per second. Negative 32 times 3/4 plus 16, that's negative 8 times 3, that's negative 24 plus 16, or negative 8 feet per second. I want to find the velocity at one point in time, take the derivative to find the velocity function, and then plug in that term. Because velocity is the rate of change in the position, or height, the derivative of the position function will give us the velocity function. couple more to answer. Anything so far? We can really just answer a whole lot of stuff once I start getting some of these applied physics questions using the derivative. A lot of interesting things to kind of calculate. When does the diver hit the water? What is their velocity at impact? How am I going to figure out how long it takes the diver to hit the water? Which function would I use? Position function or velocity function? We'll start with that. Sure. What's the height of the diver when they hit the water? Second check? 0. So just like I needed to find the time when the diver's height was 35, isn't it just asking me the time when the diver's height is 0? So I can set the position function equal to 0. It was 35, right? This is a little bit different because we're setting equal to 0, not 35. But we can factor it. I think there's a GCF I can factor out first. What divides into each of our 3 terms? Sure. Let's actually do the negative 16, since I have a leading coefficient of negative 16. When I factor out negative 16, that leaves me t squared minus t minus 2. This is pretty easy to factor. What multiplies to make negative 2 that adds up to be negative 1 if I'm trying to factor? Set our factors to 0. Where is t minus 2 equal to 0? And where is t plus 1 equal to 0? Not negative. Does negative 1 make a lot of sense? Can time be negative 1 seconds? No. So when does the diver hit the water? Which, if I go back to the graph on Desmos, we can see right there on the x-intercept. At 2 seconds, the height of the diver would be 0 feet. What's their velocity of impact? Now I know he hits the water after 2 seconds. How can I figure out how fast they're going? Just like I plugged in a quarter and 3/4, now let's just plug in 2 seconds. What is the value of our velocity function? How fast is he going at precisely 2 seconds? Our velocity function was given here. Negative 32 times 2 plus 16. Let's see, that's negative 64 and 16. That's negative 48 feet per second. Two seconds after the diver jumps off the platform, he hits the water with a speed of negative 48 feet per second. All right, last 2 to look at. What is the maximum height of the diver? What is the maximum height of the diver? Obviously, I can look on the screen. Isn't it kind of right here where he starts to change direction from going up to going down? What would the derivative or slope of the graph be as he's going up? Positive or negative? How about when he's going down? What's the slope of the graph? Positive or negative? So what's the slope of the graph when he's at the top? 0. If he changes direction and goes from going up to going down, shouldn't the slope of the graph at the vertex at the top be 0? So what we're trying to figure out is, where is the velocity equal to 0? When he changes direction, the velocity has to be 0. The slope of the graph has to be 0. So let's set the velocity function equal to 0 to figure out where the top of the diver's path is. Negative 32t plus 16 equals 0. Subtract 16, divide by negative 32. That at 1/2. Is that the answer to the question? What did I just figure out? The time it takes him 1/2 second after he jumps to be at the top. Does that answer the question? What do I have to do with the 1/2 now? Right. What's the height of the diver when he reaches the top? I know it takes him this long, so let's plug in the time to figure out that height. What is S of 1/2 equal to? Well, since I've got that pulled up, let's change this to 0.5. Is that 36? One half squared is 1/4. Negative 16 times a fourth is negative 4. 16 times a half would be 8. Negative 4 plus 8 is 4. Plus 32 makes 36. So I think that checks out okay. 1/2 second after they leave the platform, they're 36 feet above the line with its maximum height. Then they'll start turning the corner, fall back down towards the surface before they splash down. Okay. Let's think about this last one here for a second. When is the diver speeding up? When is the diver slowing down? When I think about speed, when it comes to position, velocity, and acceleration, let's talk about acceleration for a moment. What is acceleration measuring? How fast the speed is changing, right? How fast the velocity is changing. So it's feet per second per second. So therefore, the acceleration function is the rate of change in the velocity function. Acceleration is the derivative of velocity, because acceleration is the rate of change in the velocity. I put all this together. Acceleration is the derivative of velocity. And since the velocity is the derivative of the position function, the double derivative of the position function is also the same as the acceleration function. When acceleration and velocity are the same sign, speeding up. If acceleration and velocity are both positive, it means it's speeding up as it goes above the ground. It's speeding up as it's going up into the air. When acceleration and velocity are both negative, now it's speeding up as it's falling back towards the surface of the earth, right? When acceleration and velocity are both negative, it's picking up speed. It's just picking up speed as it falls down towards the ground. How about when they're both different signs, one positive, one negative? If velocity is positive but acceleration is negative, is that acceleration taking away some of the velocity every single second? So it's going to be losing speed, right? And vice versa, if velocity is negative but acceleration is positive, it's falling back towards the ground. It's just doing so at a slower speed as acceleration is taking away some of the velocity. So if velocity and acceleration are different signs, okay. Let's look at the velocity function for a minute. Negative 32t plus 16. I'm going to make a number. Where was the velocity equal to 0 at? Where does it change signs? We already got that figured out earlier. Why? At 1/2 second, the top of the path, right? That's where his maximum height is achieved. So at 1/2 second, that's where the velocity is equal to 0. What's the velocity for everything before 1/2 second? Would it be positive or negative? Before, at any time before, between 0 and 1/2 seconds. Between 0 and 1/2 seconds. Positive. Because he's going up, right? So I'm going to put a few positives here. So let me know that the velocity between 0 and 1/2 seconds is positive. I'm trying to compare the signs of velocity and acceleration. What happens to the velocity between 1/2 and 2 seconds? Because now what's happening? Down. We haven't found the acceleration function yet, but isn't it just the derivative of the velocity function? Because acceleration is the rate of change in velocity. What's the derivative of negative 32t plus 16? Which should make sense. What's the acceleration due to gravity here on good old planet Earth? Acceleration due to gravity here on planet Earth. Numerically, what is it though? Mr. Armstead has always said that acceleration due to gravity is what constant? Or in terms of feet, 9.8 meters is the same as 32 feet. Is it positive or negative? Why is it negative? Pulling you back down towards the surface, right? So between 0 and 2 seconds, what is the sign of the acceleration function? It doesn't change signs anywhere. It's always what sign? Negative. It's always negative 32. It's a constant. On what interval are acceleration and velocity the same sign and therefore speeding up? 1/2 to 2. Why did I stop at 2? That's where he hits the water, right? I don't care what happens after 2 seconds. He's already landed. Between 1/2 and 2 seconds, velocity and acceleration are the same. So what does that tell me about the diagram? Shouldn't they be speeding up as they fall back down towards splash? What happens between 0 and 1/2 seconds? He's slowing down because isn't he eventually going to turn the corner somewhere? He's slowing down as he approaches the maximum point where he turns direction. What we're going to do here is we're going to say speeding up. 1/2 and 2 seconds. Speeding up from the point where they are at the top to where they come back down towards the ground. I guess we didn't have the Olympics this last summer, but you know what I'm talking about, where they jump off the platform and then they come back down to the water and they splash down, right? They're going to be speeding up at any point between the top and the bottom, right? they're slowing down the moment they leave the platform to wherever they have their maximum point. So in this diver's case, that's between 0 to 1/2 second. And we could compare those number lines and the signs of velocity and acceleration. Let's figure it out. That took most of the time. Let me get you guys this quiz passed out before I forget.